Johnny here with Simpson Math. In this video, I'm going to talk about net change, dealing with integration. But first, let's just start off. Let's pretend I am the little dot, and I'm going to be moving in a forward direction and a backward direction. And let's just say I can move left and right. So I start here, and I move forward or in a right direction 2 units. So I start there, and I move right 2 units. And then I decide to move left 3 units from there. So end up there, and I'm moving now left 3 units, or in a backward position, I'm moving left. And then I stop. So I started here, I moved right 2, and then left 2, and this is where I end up. I'll go ahead and write stop there. All right, so we talk about distance in a couple of ways here, where total distance, how much total distance did I move? I moved 2 units right and then 3 units left, so I moved a total of 5 units. But what was my displacement? Displacement is how far did I end up away from where I started. So I'm not 5 units away from where I started, I'm only 1 unit away. So my displacement is 1, maybe a negative 1, and then my total distance is 5. Now the negative, that just means, and we're, I guess, like behind where we started. It's just a direction, helps us with the direction. So I'm negative 1, like to the left or behind where I started. Okay, let me jump to Calculus 1 when we were talking about position, velocity, and acceleration and how those derivatives affect each other. So just remember, if you have s of t, this is just a function that describes position. So time is my input. After a certain amount of time, the object has moved some distance. That's a position function. The first derivative of position is velocity. And it's that same input of time, but the derivative function, velocity, will tell us how fast that object was moving at that certain time. So after 2 seconds, maybe I had moved 2 units. Then the velocity function after 2 seconds would tell me how fast I was moving at that moment. If we were to continue, the next down the list is acceleration. Same idea. The input variable is still the time, but now the derivative of velocity, or the second derivative of position. This function will tell us the rate which we were like increasing or decreasing, that acceleration. All right, so let me draw a little picture up here of some position function and maybe its velocity function. We did this previously. Let's say I have a ball 1 meter above the ground and I throw it up and then it comes back down and I'll let it hit the ground. So here I am starting at 1 meter and I throw the ball up and then it comes back down and hits the ground. So my input axis here is time, my output is s of t, or position, distance. I'm really just looking at the y-axis though. I throw it up and then it comes back down. If I'm looking at the time, then, time and forward motion, I guess, looks something like this. I'll throw the ball up. At some point, gravity will pull it back down. It'll get to the position or that 1 meter off the ground that it started at, but then it'll continue to fall and hit the ground there. So I started at 1 and went up some distance and then came down and hit the ground. Okay, that's S of t. And from this, I can get maybe a good little sketch of the derivative function, or v of t, where again the input axis is t, but now my function, or the y values, are the velocity. And in Calculus 1, we played around with graphing a derivative function based off an original function. So one way to think about it is the slope of every single tangent line that we can draw. So this starts off as a positive slope, and then it seems to be decreasing, 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 till we get to this zero slope. At that point, the slope will change and go into the negative region, negative region. And we've graphed enough of these parabolas to know that their slope, or the derivatives, will be linear in nature. So we've got something that looks like this. It starts off positive, it gets smaller and smaller and smaller, hits 0, and then continues to go into the negative region. And you probably remember how when the original function was increasing, the derivative function was positive, or above the x-axis. When the position function, or when that original function is decreasing, then the derivative function is negative. Well, today we're going to be talking about that same idea, but now we're going in reverse. So we're starting with the antiderivative. No, that's not right. We're starting with the derivative function, and we're going to take the antiderivative to go back to the original function. So now we're going from velocity to position. So let's think about that for a little bit. When the velocity function is positive, the object is moving in this forward or positive direction. That was, I threw the ball up into the air. But when the velocity function is negative, well, then my object has started to go in a negative direction. It's now starting to fall back toward the Earth. So we're going to be doing that. We're going to be talking about a velocity function. We're going to integrate it, or at least we're going to start talking about the graph of the integral. So when a velocity function is positive, the object is moving in a positive direction. When the velocity is negative, the object is moving in a negative direction. Let me just kind of write down what I just said there. I said when the position function is increasing, that implies that the velocity function is positive. So it's decreasing, it's negative. And then the other direction around, when velocity is positive, then the object is moving in a positive motion. I'll put motion as positive. All right, before I get to our first example, just in my notes here, I'm going to say back in the day when I was in school, I learned that when you let go of an object, the Earth pulls that object down at an acceleration rate of negative 32 feet per second squared. Depending on what Google says or what your physics teacher says, maybe you know that as negative 9.8 meters per second squared. But I think there's a few problems in the homework where I just ask you about velocity, but I don't really give you any information. So if you just use the fact that the Earth pulls an item at this rate, I think you can answer the questions. All right, let's move on to our first example. All right, we are given a velocity function v of t, 10 sine double angle on this interval from 0 to 2 pi. Okay, part A. Graph that function, okay, and determine when the motion is positive or is in a positive direction and when it is in a negative direction. Okay, yeah. So if I can get a picture of the velocity function, then I can decide when it's positive, the object was moving in a positive direction, and when the velocity function is negative, the object is moving in a negative direction. So I just need to graph 10 sine 2t. Oh yeah, I know how, these are just transformations. The 2t means that the sine wave is going twice as fast, so all of those x values will be like I maybe multiply by half. And then the 10 just changes the amplitude. Instead of going to a maximum of 1, I'll go to a max of 10. I'd call that a horizontal compression. It's going twice as fast. And then we have an A transformation. That's the amplitude out front. The amplitude is now 10. Or I need to multiply those y values by 10. But sine waves are easy to graph. You just graph a sine wave and then label accordingly. So it does want me to graph the thing from 0 to 2 pi. So I teach my trig students just to go by pi twelfths. That seems to be easy. So kind of like skip, dash, 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 skip, dash. That's pi halves. Skip, dash, 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 skip, dash. There's 1 pi. Do that one more time. That's 3 pi halves. Skip, dash, 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 skip, dash. There we are at 2 pi. And normally sine takes 2 pi to complete its cycle, but I'm going to complete one period within 1 pi. And my max value here is 10. So I divide by 6, it's going to be half. Something like this. There we go. I have graphed 10 sine 2t. No, I didn't. I graphed 10 sine t. Let me change color and fix my mistake. I'm going twice as fast. So I should be done by the time I get here. So I should be 0 there. So at pi fourths, I should reach my maximum. So here we go. In red, I have 10 sine 2t. In black, what I did is I started off with a parent and changed its amplitude. So in black, I have 10 sine of t, not faster. All right, so I've taken care of the graph, and now I can see where the velocity function is positive from 0 to pi halves, and where, oh, but it doesn't want me to show 2 pi. Okay, I'm not done yet. Because it asked me to graph it over its interval. So I've shown one period, but I need to continue on to 2 pi. Oh my gosh. There we go. Okay, what was I saying? Oh yeah, where the velocity function is positive, the object was moving in a positive direction. So let me just plot that down before I make another mistake. The motion is positive wherever the velocity function is positive. So from 0 to pi halves and from pi to 3 pi halves. Oh my gosh, 3 pi halves. That is just a mess, but that's going to be in parentheses. Okay, and it will be negative along the interval pi halves to pi union 3 pi halves to 2 pi. Now, I'm using open parentheses here because at pi, I am not moving in a positive direction nor a negative direction. So I cannot use brackets to show inclusion. So these intervals of motion will be using open parentheses, no matter what. Okay. Let me walk through that again. I was a little confused the entire time. I was given a velocity function. I graphed it in red. Where it's positive, that's where in the original, like a position function, I don't have that, but where that item is moving in a positive direction, and then when the velocity function is negative or below the x-axis, that's when the item is falling or going backwards or going in a negative direction. Okay. Let's add a part B to this problem where we just want to find the displacement. Now, finding displacement is finding the distance that we moved, but we only care about how far we are from where we started. So if you think back to my little dot, we're not talking about the total distance of 5, we're talking about just the distance we were away from the start. So the distance is the same thing as the displacement is the same thing as net change. And hopefully you can tell from this graph the answer already. With this velocity graph, the red graph, I can tell that the object went in a positive direction and then it came back down to where it started. It went in a negative direction and then it went back to where it started. It went in a positive direction, came back down to where it started. Went in a negative direction, came back down to where it started. So notice I ended up exactly where I began. This displacement, in the end, better be 0. But I would like to use this like trivial or maybe obvious example just to show you the calculus or the math behind it. So in the end, our answer better be 0, otherwise, like our understanding is not quite right. Okay, displacement. How do we find that given this velocity function? We weren't given a position function, we were given a velocity function. Well, displacement, we can think about that as net change. Net change is the amount of change like away from 0. Let me think about this. If I were to find the antiderivative of velocity, that would get us back up to the position function. Let's just start there. I'm going to set up an integral on our interval of interest 0 to pi. I'm integrating our velocity function 10 sine 2t with respect to time. If I integrate this velocity function, it will spit out the position function. And if I evaluate that thing from 0 to 2 pi, it's telling me two things. It's telling me the area, like the shaded area of this graph, but it's also telling me the change in position, that net change in position. So let's think about the area for a little bit. I have a picture of it, so it should be obvious. That shaded area and this shaded area will net to 0. That shaded area and this shaded area will net to 0. Also, though, this is talking about the antiderivative. Let's go find that derivative. Maybe if I have a picture of it, I can talk about it more easily. Okay, I know how to do this. The antiderivative of sine would be a cosine. The argument's going to stay the same. This is going to be cosine 2t with a negative 1/2 out front, and I still have that 10 coefficient. But I need to evaluate this thing from 0 to 2 pi. Well, that's just negative 5 cosine double angle. I'm supposed to evaluate this thing from 0 to 2 pi. Okay, I can do some algebra here. This is cosine double 2 pi minus cosine double 0. Well, cosine 4 pi is 1, 2, that's 1, and then cosine of 0 is also 1. Oh, let's see. So I have negative 5, 1 minus 1, yeah. Oh yeah, 5 times 0, and that's that 0 I knew that we should get. Now let's get a picture of negative 5 cosine 2t so we can talk about this position function. I could graph it here. It's got an amplitude of 5 now. It's a cosine going twice as fast, but I think Desmos will help me talk about this. Let me switch over to Desmos. Let me type in our velocity function. 10 times sine of double angle. And I only care about that interval from 0, let's see, less than or equal to x, which is less than or equal to 2 pi. And then let's get its derivative up there. So the antiderivative, negative 5 cosine double angle. Let's give it that same interval. 0 is less than or equal to x, which is less than or equal to 2 pi. I'm going to come over here and clean this up a bit. I'll come to this wrench and say, let's make our y-axis the radian axis, or at least talk about it in pi 12th steps, maybe. That work? Did not work like I wanted it to. Oh, not the y-axis. Oh my gosh. How about the x-axis in pi 12ths? Why am I having problems? I don't want you to label it. Oh my gosh, I'm going to go crazy over here. Much better. Okay, that y-axis is kind of hard to see when it's zoomed out like this. I wonder if I can say, let's go from 0 to 2 pi, if that clears things up. Did I not type in 0? Okay. That's better. That's what I wanted. Okay, in blue, I've got the freaking velocity function. In green, I have the derivative, which was the position function. Okay, when the velocity function was positive, so from 0 to pi halves, the antiderivative, the position function was moving in a positive direction. Yes, from 0 to pi 12ths, notice the green function, which is the position function, is moving in that positive or increasing manner. Then from pi halves to pi, the velocity function, which is blue, is going in is all below the x-axis, meaning the position function is now like that object is falling or going in reverse from pi halves to pi. Good. Okay, what were we talking about? We were talking about displacement. Okay. So yes, notice the object started here at negative 5. It went up to 5, back down to negative 5. Up to 5, back down to negative 5. So after going a time of 2 pi, the object is just back where it started. This is like a pendulum. So it's swinging back and forth. It's going in a positive direction. It's going negative. It's going forward. It's going negative. Every pi, it just goes back to where it started. Okay, I think I've got my head wrapped around that. Now I'm going to go back now to this. Did that answer the question of whatever I was asking myself? I think so. That's displacement. So the y-axis, I was back to where I started. Now, if I asked for the total distance, that's a different question. If I want the distance, then I'm going to have to find, that distance, add this distance, add that distance, add that distance. So the way we do that, I'll do a part C and I'll say, well, what was the total distance traveled? Well, if I look at the velocity function, so let me get rid of the position function. If I'm looking at the velocity function, then the total distance is, I think of it as that area. I need to add up all those areas. So I need to calculate the area of this hump. That's calculating the area, but it's also calculating that net change in the antiderivative. So we're looking at a velocity function, but if I calculate that area, that's calculating the that net change in the position function. Okay, so I need to calculate that area, this area, that area, and this area. Now, one clever thing to do would be to acknowledge that these are just the same thing. So if I could calculate the distance from 0 to pi, I could then double it to get all of this. I cannot do that. I could do that from 0 to pi halves. I could find that little area and then quadruple it, as long as I'm aware that this is going to be negative. Okay, so let's do this. I'm going to set up an integral. I'm going to go from 0 to pi halves. And by calculating that area, everything is fine. Then I'm going to do something to another interval from pi halves to pi. And there's two ways to handle this algebraically. I'm going to be adding this other distance. So you could add and then absolute value that result. And that is because I know this area, when I calculate the integral, is going to give me a negative. It calculates the area below an x-axis as negative area. So I need an absolute value. Or you could subtract knowing you're going to get a negative number, so you're subtracting that negative value. And then we just have these to calculate real quick. I already said the integral of this is -5 cosine 2t. We're taking that and we're evaluating it from 0 to pi halves. To that, we're going to add the absolute value of -5 cosine 2t being evaluated from pi halves to pi. So at this point, it's kind of tedious, but we just kind of go with it. -5 times cosine double pi halves minus cosine double 0. This is being multiplied by a -5. To that, I'm going to add the absolute value of -5 being multiplied by cosine double pi minus cosine double pi halves. Okay, well, cosine pi is -1. Cosine 0 is 1. Cosine 2 pi is 0. No, sorry, positive 1. And cosine pi is negative 1. Clean this up. Negative 5 times negative 2 is positive 10. And negative 5 times 2 is negative 10, but I'm going to absolute value it, get 10, and get 20. Now this is only the distance from 0 to pi. So I need to double this. And I get 40 units. Now let's go back to my graph and let's make sure that makes sense. Let me get on there the position function again. I deleted it. It was a mistake. Let me put it back on there. I'm putting the position function negative 5 cosine double angle, and I really want to see this just along this interval. And this 40 should make sense when we talk about distance traveled. So I started down here at negative 5. From there, I went up to 0 and then up to 5. That's a distance of 10. Don't you agree? Continuing with the distance, I move downward 5 and 5 more. So that's another distance of 10. So that's a total distance of 20 that we have traveled. When I double that, I get a distance of 40. So I didn't need a picture of the position function to talk about that distance change, or that net change in distance. I was able to do it just with the integration process. Bam. All right, that's the main idea. I know I've not done the best job of explaining it, but maybe some more examples will make it clear. Oh, there is one thing I want to talk about. Finding net change. There's actually like 2 ways to talk about an antiderivative. Okay, let me take a look at that. All right, so we just talked about finding that position function using the antiderivative. We've done this plenty of times, but let me write that down one more time. If I have some integral from 0 to t of some velocity function then let's see, that integral from 0 to t of v of t. V of t, I'm trying to think of it this time as an antiderivative. Velocity is the same thing as the derivative of position. I've got it stated right there. So I'm going to say this is the same thing as the integral from 0 to t of s of t, f prime of t, sorry, s prime of t dt. Then we use that fundamental theorem of calculus to say, well, this is equal to s of t. The integral and the anti-integral cancel each other out, leaving me with the position function that I'm supposed to evaluate from 0 to t. Okay, so that's just, I'm going to the position function, plugging in t, and subtracting the bottom, or that initial position. Okay, when all of these say the exact same thing, when I see this, when I see the integral of some function, in my mind, I see area. I see area between the curve of the function and the x-axis. And the integral is calculating that net area. It's taking the positive areas and it's taking the negative areas, and it's kind of like netting them out, and you're just finding that area. So this to me is net area. I changed the velocity to the antiderivative position. Now they're the same thing, but to me this is now talking about something completely different. This is now talking about, like, the S prime is the rate of change in which the position function is changing, so the rate of change. But then the antiderivative is then calculating the net area of that rate of change of the position function. Let me write that down. So it's like I have some function, let's say it's some v function for volume, and this function calculates the volume of, I have no idea, oh no, something crazy, the volume of a balloon. I'm not even sure how to spell balloon right now. So the volume of a balloon, if that's a word. And then I say, well, okay, what is then v prime? Well, v prime, that function, is calculating the rate at which the volume is changing with respect to time. So as time goes on, is the area, the volume of the balloon getting bigger, and at what's that rate of change? If I then undo that, if I'm integrating that rate of change, then now I'm talking about that net rate of change. So here, it's the net change in position over time. And this is just the fundamental theorem of calculus. But notice what this is talking about. This is talking about S of t. This is the net change in the function itself. So when we were looking at we were basically just looking at the y values. I looked at the -5, we went up to the +5, back down to -5. We're only looking at those y values. So this is it's just net change. That's all it is. And because we're talking about that position function, it's just, what did I start off? Where was I when I started? And where was I when I stopped? That's all we had to do. I found, like, I started at 0 and I stopped at 0. So then my net change is 0. All right. Let's see. Oh, let's go with this idea of these are all the same freaking thing. And let's do the front one and the back one, and let's talk about that for a little bit. The integral from 0 to t of v of t in the end is just calculating, using the fundamental theorem of calculus, the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Now notice there's a st right there. What is s of t? S of t is simply the antiderivative of v of t. So in the homework, I have you find the antiderivative, which we've been doing all semester long, but a new way to maybe think about the process of finding the antiderivative is just using the fundamental theorem of calculus and then solving for s of t. So if I want s of t all by itself, I'll just need to add s of 0 to the other side of the equation. Now what is s of 0? If s of t is a position function, then s of 0 is the position when time was 0. This is an initial value, where we started. So I'm just going to add this initial value to the other side of the equation. One way to find or talk about the antiderivative is just plugging in an initial value and adding the integral from 0 to t of the velocity function. So I believe in the homework I say find the antiderivative, do it, or I'll ask you two ways. I'll say use the antiderivative and then use the fundamental theorem of calculus. So here is the fundamental theorem of calculus, and here is the antiderivative. All right, Our next example starts off the same. They've given us a velocity function, negative t cubed plus 3t squared minus 2t. They've given us an interval from 0 to 3, and they've given us an initial position. So when I plug in 0 to the position function, I'm starting at a 4 position. Okay. But part A simply says graph this velocity function, and then based off the graph, was the object moving in a positive direction or a negative direction? So I need to graph this cubic. Okay, well, it factors, so I think I can find the x-intercepts very quickly. I'll set the equation equal to y, or the y to 0. I'll factor out a t. I'll factor out a negative t, actually. And I'm going to get t squared minus 3t plus 2. That's a trinomial. I think it factors, yep. So I'm going to continue factoring. Trinomials factor to the product of two binomials. T and t, 1 and 2, the signs are the same, they're both negative. So I can tell this graph will cross the x-axis at 0, 1, and 2. All of those are in my interval. I think I can sketch this out. So it starts at the origin. I know this is cubic in nature. It has a leading coefficient that's negative, so it will fall on the right. It's an odd power, so it has opposite in behavior, so it's rising on the left. It's a cubic, so I'm expecting these two turns, and because of these x-intercepts, I'm pretty sure that it does. All of these x-intercepts have a multiplicity of 1, which is odd, so I know it's crossing at each of these x-intercepts. And so I'm just hugging the x-axis now. What happens at 3? If I plug in 3, I'm going to get another point in here. V evaluated at 3 is negative 3 cubed plus 3 times 3 squared minus 2 times 3. Let's see, 3 cubed is 27, so this is negative 27 plus 27, that's convenient, minus 6. So there is a point at 3 comma negative 6. I'm not sure how high it goes. I could plug in a 1.5 maybe, but I think I got the idea. I know what's going on. I just need to know when is this thing positive and when is this thing negative. I can tell it's 0, 0, 1, 0, 2, 0, and then here's 3. I will be doing something like this. That is mine. Stops at when x and t is 3. This is v of t. I don't need to get too more, like I don't have to be nitpicky about how far I go up. Of course I have taken calculus, so I could do that, but I just want to know when is this thing in a positive direction. So I am moving in a positive direction when the velocity is positive. So that's from 1 to 2. I'm in a negative motion, or I'm like moving in a negative direction, as I start off from 0 to 1, and then from 2 to 3. Okay, I've answered part A. Graphed it on that interval based off whether the velocity function was above the x-axis or below the x-axis. I was able to tell when the object was moving in a positive direction versus moving in a negative direction. This is a velocity function, but I'm able to talk about the position function. All right, let me throw in a part B. All right, Part B says determine the position function. So they gave us a velocity function and they want us to determine what the position function was. And they say use both an antiderivative and the fundamental theorem of calculus to do this. And since you're doing it two different ways, make sure those two answers are agreeing with each other. Now, we know how to find an antiderivative. It's just the integration. There is an issue here, though, because of the plus c. When we integrate v of t, we're going to get a s of t with a plus c. But I'm going to show you how to handle that. So let's first go about this using the antiderivative method. You already know how to set this up. We are integrating from 0 to 3. Actually, no, I'm just integrating. I'm just trying to find the position function. It does say for like any t value. So I'm just finding the position function, not over an interval. Just trying to find the position function. So I'm integrating my velocity function, negative t cubed plus 3t squared minus 2t with respect to t. This is going to give me s of t, the position function, by integrating the velocity function. Okay, integration is a linear operator, so I can do these kind of independently. And these are all power rules. I'll have a negative 1/4 t to the 4th plus, all those reduce, so leaving me with t cubed minus, that reduces, t squared, and then I would have a plus c. Okay, so that c now is a thing to worry about. Oh, but wait a second. I know s of t is this function, and they gave me an initial value of s of 0 is 4, meaning when I plug in a time of 0, the output better be 4. So I claim s of t is negative 1/4 t to the 4th plus t cubed minus t squared plus c, and I'm going to evaluate my function at time 0. Okay, I'm evaluating this at time 0, meaning I'm going to go through and I'm going to replace all of my t's with 0. Oh, and I know s of 0. S of 0 is given as 4. So in the end, this has got to be equal to 4. The right-hand side is very convenient. All of those zeros are convenient in that polynomial, leaving me with c equals 4. Now this is not always the case. You could see like in an exponential function where I give you an initial value, s of 0 equaling 4, then e to the 0, that's not going to go away. I'll have e to the 0, which is 1. So that's not always so convenient. S sub 0 equaling 4 does not mean c is 4. You kind of have to go through this process every time. So use the antiderivative, or the integral process to find the antiderivative. Shove in your initial value to find c. So now I feel comfortable saying s of t is equal to a negative 1/4 t to the 4th plus t cubed minus t squared plus my c value of 4. Some of the homework problems where I have you find the antiderivative function that's not position and velocity, I have to give you that initial value in order to finish the problem. So most of the problems will give you some sort of initial value. If it's not stated, reread the problem, make sure it's not stated. But if it's not stated, you may assume that initial values are 0. That's for my problems only. Okay, let me now find the same position function, but I'm going to use this time the fundamental theorem of calculus. So we said last time, another way to find a antiderivative of the position function is to take the initial value, which was given to us, and then add a definite integral from 0 to t. So this was an indefinite integral we did, but we were able to calculate the position function. We're going to find that same position function using a different method. S of t will be equal to the initial value plus the integral from 0 to t of that velocity function. Negative t, or let me use x's, I don't know, t cubed plus 3t squared. I'm thinking I should use x's here. Oh well. 3t with respect to t. Make sure that makes sense to me. Alright. Well, this was given to me. That's 4. S of 0 is 4. And I know how to integrate this. In fact, it's going to be the same process. I'll just have some limits of integration to deal with. So this is negative 1/4 t to the 4th power plus, no, that goes away, t cubed minus t squared from 0 to t. I now need to apply the fundamental theorem of calculus, plugging in the upper limit and subtracting the lower limit. Well, again, this is a polynomial, so all of those zeros are going to be very nice for this particular problem. I'm just going to put a big fat 0 there. All of these plugging in a 0, I'm just subtracting 0. So I am done. I get 4 minus 1/4 t to the 4th plus t cubed minus t squared. That is my antiderivative, or my position function. It's just the initial value plus the antiderivative from over that interval 0 to t. These should match. The only difference is I put my 4 out front. But plus 4, same thing. Alright, let's look at what's going on visually. So I'm going to graph the position function, and I'm going to graph the velocity function, and I'm going to see if it's true. All I have to do is look at the y-axis. Alright, let's go off to Desmos. Let me clear these out. I'm going to type in the velocity function first. That was the negative t cubed plus 3t to the 2nd power minus 2t. And we graph this. Oh, sorry, Desmos. We graph this, and let me change my y-axis back to what it should be. Let's just use normal numbers here. There we go. That looks good to me. And that's what we graphed. We said from 0 to 3, it looks just like that. I don't mean on this axis. Okay. Perfect. Now, I'm going to now graph the position function, which we just calculated twice, and we said it is negative 1/4 x to the 4th power plus t to the 3rd power minus t squared, and we had an initial value of plus 4. There we go. Okay. Now notice the plus t is not all that important, actually. Because we're just talking about the change in position. So here I have in black a position function. I started at a y value of 4, and I want to know what was my displacement after a time of 3 seconds. In fact, let me cut this off at 3. All right, so what was my displacement after 3 seconds? So notice I'm starting at a y value of 4. On the position function, I'm starting at 4. I go in a negative direction down this little bit, but then I just go back up to the 4. So after 2 seconds, I'm back to 4. I'm back to where I started. After 2 seconds, I have not moved, basically. I went to the H-E-B, did some grocery shopping, and I came home. I'm back where I started. Then, in the last second, from second 2 to second 3, I go from 4 down to what looks like about 1.75. So that displacement is just 2.25. Oh, I could plug in some stuff if I needed to. Did I ever do that? Okay. So, in fact, let's go do that. I'm going to go back to my antiderivative, and I'm going to plug in a time of 3. I'm going to evaluate this thing from 0 to 3 and find that net change. But looking at the graph, I can already see, I think it's about negative 2.2, negative 2.25, something like that. And I wanted to show that the plus 4, or that plus c value, doesn't matter. If I move that to be plus 6, notice the shape didn't change. And I don't care how far I am away from the x-axis. This time I started at 6 and went down a little bit and back to 6. No change after 2 seconds. Then in the last second, I went down from that 6 position to what looks like 3.75. So that's that same negative 2.25 or whatever it is. If I have no c at all, the graph is just shifted all the way back down to the x-axis. It's hugging it. So I go down, up, and then down what looks like about negative 2.25. Let me fix my graph just so I don't get confused, and then go back to my work and let's do some arithmetic. I want to know, or basically I'm not done with this question. Is there a part D? Or am I just making that part D yet? Let's do it. Let's find the displacement. That is, I'm going from 0 to 3. I want to know, in those 3 seconds, how far did I move? I'm going to plug this into the antiderivative of velocity, which I'm calling the position function. I just need to plug in a 3, and I need to plug in a 0. I'm going to use this version right here. Plug in a 3. Oh, I feel like I've done this before. This is 4 minus 1/4 of 3. No, I don't want to use this initial stuff. I'm not doing that. That would be fine. I just want to use that. All right, so I need to, that was right there. I need to plug in the 3 and plug in a 0 and then find that subtraction. So here we go. This is S of 3 would be 4 minus 1/4 of 3 to the 4th power plus 3 cubed minus 3 squared. Okay, I can do this. That is 81/4. Gross. This is 27. And that's minus 6. And that is 31 minus 6 is 25. Use a calculator. I get 1.75. Okay, now I need S of 0. Actually, I know that value. It was given to me. S of 0 is 4. We did calculate that earlier. Let me plug 0 into the position function. I'm left with just 4. That was easy. So what I'm trying to find is 1.75 minus 4, which is negative 2.25. Negative 2.25. The antiderivative of velocity, that antiderivative process, is giving us a net change of negative 2.25. If I was given the velocity function, then we're talking about the position changed, a net change of negative 2.25. That's exactly what we were saying. Starting here at 4, I ended up at 1.75. That is a net change of negative 2.25. Now what if I wanted the total distance traveled? That doesn't account for this backwards motion and then forward motion. So how do I find the total distance? If I want to find the total distance, I'm going to have to break up my integration process. I need to go from 0 to 1, integrate that, absolute value that, or somehow make that distance, that area positive. Do that again from 2 to 3, it will be positive. And then from 2 to 3, I need to do that again, and I need to absolute value that as well, because it's going to calculate as negative, and I want to know the total distance, so I need to make all these areas positive. So first let me just kind of set up what's that would look like. I'm integrating the velocity function from 0 to 1. This is under the x-axis, so I need to absolute value bar that. To that, I'm going to add the integral from 1 to 2 of the velocity function. This, I have a picture I know is above the x-axis, so I don't have to worry about absoluting it. And I'm going to add the last integral from 2 to 3, but this is needing to be absolute valued because it is negative or below the x-axis. Now, I know that these two integrals are actually the same because of how polynomials work and their symmetry. So if I could just find this one, I think I could know the answer to this question. So if I want to do this, that is, I need to find the antiderivative, plug in a 1, and subtract in the antiderivative the lower bound 0. I found this already, so I'm just going to go through and plug in a 1. This is negative 1/4 times 1 to the 4th power plus a 1 cubed minus a 1 squared. And then from that, I need to subtract the initial position, or that 4 value. I wouldn't have to include the c here, but let's do it. Okay, well that's 1 minus 1. These two cancel each other out. So really all I'm having to worry about is this negative quarter. In fact, I don't want to include this c value. This c value will be there in every single process, and in fact, oh yeah, because it's a definite integral, there is no c value. What am I talking about? This is fundamental theorem of calculus. We don't worry about the c value. It would be fine. It would, if I put them in every single one, I think it would turn out fine. But yeah, I'm just using fundamental theorem of calculus. It's just negative 0.25. Don't worry about it. Now I'm supposed to absolute value bar that. So that first little hump means that I went in a negative direction 0.25 units. I know this one is identical. I could do the same thing. Plugging in a 2, subtract plugging in a 1. I know that polynomials are symmetrical though, so it's going to be another 0.25. Or basically I undid it. I went down, and then I went back up, and then back to 0. That up and down was the same distance. Plus this last one, which we already know is 2.25. So my total distance is 2.75 units. Like I did everything associated with that one problem, but hopefully you've followed along. I was given velocity, I graphed it. From the graph, I can talk about position moving in a positive direction versus a negative direction. Good. Then I said, well, what was the antiderivative. So I found that two different ways. Old school way, just finding an antiderivative with a new twist, because in order to find that antiderivative, I had to know the initial value. So we talked about that. And then finding that antiderivative using the fundamental theorem of calculus. That was a new little experience. Then I went back to the distance idea, the net, like the displacement versus the distance. Total distance, you have to break up the integral. If you're just asked for displacement, it's kind of easy. You just anti-integrate, anti-differentiate. You integrate. Brain dead. Go away. Bye.